Okay, so this method for volumes of revolution. Okay, so now what is this going to correspond to? You have some type of function that you want to revolve about the x-axis, okay? So call that f of x. This is the same with x, it's just down here. Okay, so when it comes to the disk method, this is going to be the integral from a to b of pi f of x squared, okay? So what are you doing? You're essentially, what is this corresponding to? This is corresponding to pi r squared, okay? So what you're doing is you're taking a circle whose radius is corresponding to the height of the function. So you can see that this height right here, the radius of this circle, is corresponding directly with the function. So you're taking a circle and you're starting at A and you're pushing this circle all the way down until you get to B. And by pushing this two-dimensional object down the line, it's creating a three-dimensional volume, okay? So remember when we were in Calculus 1, you integrated a line and you got area, okay? Well, what happens when you integrate area and push area down a line? Well, it's going to create volume, okay? So I'm going to start off with one of the classic problems. This is going to be a little advanced just because it's an improper interval, but we'll be covering improper intervals in this class anyway. So this is a good place to just go ahead and show it. So what is the problem that I'm talking about? Gabriel's horn. So weird things happen when you go off to infinity. So So if we just take the function 1 divided by x and we rotate it about the x-axis, okay? We're going to take that circle And we're going to just go ahead and we are going to push it down that line all the way from 1 to infinity. Okay? So we're going to start here at 1. Okay? So the volume of Gabriel's horn Now, I know we haven't gone over improper intervals yet, but whenever you have intervals that end up incorporating infinity, you got to stick a limit on it. You have to evaluate it as a limit. Okay? So, this thing is going to equal, now the limit, as b tends towards infinity, the interval from 1 to b, I'm going to write it like this, pi, 1 over x squared, yes. Okay. All right, now this is just going to be the power rule. So if we have 1 divided by x squared, that's really x to the negative 2 power. So what happens when I integrate x to the negative 2? It's got to go up by a number and divide by that number. So the integral of x to the negative 2 would become x to the negative 1 divided by negative 1. Okay, so this is going to equal the limit. Now as b tends towards infinity, this would be negative pi divided by x, evaluated at 1 and at b. Okay. So that will equal the limit as b tends towards infinity of negative pi divided by b, and then plus pi divided by 1. This term right here will go to 0. The answer is pi. Okay, so it's pi. What makes this like, why would somebody give this a name? That would be the question. So why is Gabriel's horn called Gabriel's horn? Because Gabriel's horn has a very strange property to it. We probably won't do this problem when we get to surface areas because it's pretty long. But even just calculating, if you were going to calculate the area of like a little wall inside of here, it will end up being infinite. So if you calculate the surface area of Gabriel's horn, it's infinity. But if you calculate the volume of Gabriel's horn, it's pi. Now, think about the implications there. It has an infinite surface area, so it takes an infinite amount of paint to paint it. But it only holds a finite amount of paint. We'll say that again. It takes an infinite amount of paint to paint it, but it only holds a finite amount of paint. And this has to do with the property of switching between dimensions. So the painting the outside of it is a two-dimensional thing, whereas the volume itself is a three-dimensional thing. So switching in between to a higher dimension creates this type of, I guess you can call it a paradox. This is not the only object that does this. It has this type of weird property. In certain fractals and other mathematical objects, something similar can happen. As an example, and this also has to do with the behavior of infinity. And so this also has to do with, if you look at the Koch snowflake, which is a fractal, if you actually take the Koch snowflake to infinity, you end up with, it has an infinite perimeter, but only a finite amount of area, because you just keep adding perimeter and perimeter to it. So the perimeter becomes infinite, but it only holds a finite amount of area. Okay.